Hi, in this video we are going to talk about another example for the red-black trees. So, let's suppose that we have a valid red-black tree with the root node 32, the root node has to be black. Every path from the root node to the leaf nodes has to contain the same amount of black nodes. And as you can see, every path contains exactly 2 black nodes. And every red node must have 2 black children. And basically because we assigned the null pointers to the leaf nodes with the color black, this property is going to be valid as well. So this is a valid red-black tree. And we would like to insert, for example, 12. We come to the conclusion that 12 is smaller than 32, so we go to the left. 12 is greater than 10, so we go to the right. 12 is smaller than 19, so we go to the left. And 12 is smaller than 16, so we insert this 12 to be the left child of the 16. And every new item we insert has the color red. And okay, on every iteration we have to check whether the red-black tree properties are violated or not. So we come to the conclusion that in this case, the red-black properties are violated. The red node 16 has a single left child 12. Okay, so basically this is the case 1 situation. We just have to recolor the nodes like this. And we have to check recursively whether with the help of this recoloring operation, maybe in other parts of the tree we have violated the red-black properties. And yeah, it is true because here, for example, in this case, we have violated the red-black properties, and this is the typical case 2 situation. We just have to make a left rotation on the node 10, like this. And again, we have to check, okay, whether is it a valid red-black tree? No, it is not a valid red-black tree because, for example, the node 19, which has the color red, it should have 2 black children, but the left child of 19 has the color red. So it is not a valid red-black tree. Okay, so we come to the conclusion that this is the case 3 situation. So we have to make a right rotation on the root node. And after rotating right and recoloring some nodes, because we have to recolor, for example, the previous root node, which is the 32, to be red, as we have seen in the case 3 situation, after it's going to be a valid red-black tree. The root node is black. Every path from the root node to all the leaf nodes contains the same amount of black nodes. To be precise, there are 2 black nodes in every single path from the root node to all the leaf nodes. And every red node has exactly 2 black children. Okay, maybe you would come to the conclusion that, for example, the node 12 doesn't have any children at all, but that's what we have been discussing, that we assign the null pointers, and the null pointers has the color black. So basically, it is true that every red node in this tree has exactly 2 black nodes. Okay. So basically I showed you this example to see that, okay, after making a single rotation or a recoloring operation, for example, we have to check recursively whether we have violated the red-black properties in other parts of the tree, because this is what's happening here. We have made a single recoloring, and with the help of this recoloring, we violated the red-black properties in other parts of the tree. Okay, we have made a single left rotation, but with this left rotation again we have violated some other red-black properties, so we have to make a final right rotation with some recoloring. And basically, with the help of these 4 cases, we have been specifying the case 1, case 2, case 3 and case 4. Of course, every case has symmetric partners, but anyways, with the help of these 4 cases, we are able to make sure that a red-black tree is going to be valid after rotations and after the recoloring operations. Thanks for watching.